All right, so just to introduce myself, I'm Han. I'm working for Nethermind. So for today's topic, this topic is going to be more on core protocol, like the technical stuff on Ethereum. So hopefully it's not very boring to you guys who are might not be non-technical, but I'm going to try this, make this session as beginner-friendly as possible. So I'm going to talk about everything you need to know about state expiry, the problem that it's trying to solve, the different solutions that we have had throughout the years, and also the evaluation of those solutions. So without further ado, let's start right away with just understand what is the state. So when we talk about state on Ethereum, we are referring to the MPT of the world state on Ethereum, right, which is the Merkle-Patricia Tri. So on Ethereum, a state is represented by two-layer MPT. So the first layer is account tri, and down there, the second layer is the so-called storage tri or the contract tri. So let's start with the account tri. So at the leaf node of the Merkle-Patricia Tri, which is the data structure, you have the account object. So on Ethereum, you have two types of account. The first type of account is called EOA, externally owned account, and the second type of account is called contract account. So now let's move on to the second layer. So for each contract account, it will also has its own Merkle-Patricia Tri. So it's the same tri as well. It's just the leaf node here will represent the value to the slot of the contract. So one key thing here that you have to understand is that the number of slots can so-called infinitely expand up to 2 to the power of 256. So to give you an example of how large 2 to the power of 256 is, basically, it is almost the number of atoms, if not more than the number of atoms in the universe. So that's why I say it's infinitely expanding. And at the same time, the number of accounts can also infinitely expand up to 2 to the power of 256. So when you combine these two information together, it basically just states that the state on Ethereum can grow infinitely, just keep growing without stopping. And under the hood, when we talk about software implementation, basically the clients like Go Ethereum or like Nethermind, everything is represented in the database as key value pairs, usually. So for example, here, just a very simple example, you have an account hash, which will map to the account object, or you will have a storage slot hash, which will map to the storage slot value. So you can think of a key value pair as a data representational unit in the a software level. Yep. So when Ethereum started with the Genesis block 0, it has a set of key value pairs. As time goes on, even now when we are talking, the key value pair number of key value pairs just increases. And right now, I think Ethereum has about 1.2 billion to 1.5 billion key value pairs, which is still going to increase in the next few years. And this phenomenon of state being keep increasing and the number of key value pairs increasing is known as the state bloat issue or the state growth issue. So why state bloat is bad, right? So let's say the state of Ethereum, or not just Ethereum, any other blockchains grows larger, it will cost more to operate a node, right? Right now, let's say I'm a home staker. The recommended hardware requirement to run a node is about 2 terabytes SSD. Next year or 2 years later, it might increase up to 2.5 or 3 terabytes. And down a decade later, it could be 10 terabytes, who knows, right? So as a home staker, you would naturally feel less incentivized to run a node because you have to keep upgrading your software from time to time, right? So it's just not feasible. And when less people will want to run a node, eventually it will lead to centralization, because those people who will run a node are the ones that has the financial capability, financial incentive to do so. And it's not just about this scenario of centralization or less people running nodes. It's also about performance of the chain. So to quote Peter from Go Ethereum, Ethereum isn't slow because of gas. Ethereum is slow because the state grows like crazy. So no matter how much the client teams optimizes their software, the state of Ethereum puts a bottleneck or a cap on how fast the software can be, right? So if we want Ethereum to be a super performant chain, this is the problem that we need to solve first. So let's look at a few solutions that clients have done to optimize their software in order to tackle this so-called state bloat issue. The first feature that I'm going to talk about is by Go Ethereum. So again, it's going to be very technical, but I'm going to simplify this. So they have released a feature called path-based state scheme. And previously, the state scheme that they use is called hash-based. What's the difference between hash-based and path-based? To put it simply, when we have the hash-based state scheme, if you're running a node, you will have to do something called offline pruning. Offline pruning means that, let's say you run a node for a few months continuously, you have to stop your node and execute a certain command to do offline pruning. After that, you have to start a node again. So this operation is called offline pruning, right? So in terms of user experience, it's really bad because you don't expect, we shouldn't expect users to stop the node and execute a certain command to do something and restart it again every certain interval. Ideally, users should let the software keep running until, for example, perhaps if the client releases a new version that's better, then it makes sense to upgrade the node, or if maybe there's hard fork, right? Then it makes sense to restart the node again. But in this case, it's not. So for path-based, it solves this issue of like having to restart the node to do offline pruning. And it also improves the performance a little bit. So that's Go Ethereum. Next, we will go to Nethermind. Oops. Yeah, Nethermind. Nethermind has 3 approaches that they have tried, right, or we have tried. So you can scan the QR code to read the article to learn more about it, but I'm just going to go through like each of them just as a summary. So the first approach is called Paprika. So Paprika is an experimentational storage engine specifically for Ethereum state. So right now, the client teams are using, for the databases, is always going to be key value pair database. So for example, LevelsDB, RocksDB, or CockroachDB. But why use a generic key value database when you can just rebuild one specifically for Ethereum? It's going to be more performant. So that's Paprika. The second approach is called path-based storage. So it's exactly the same as Go Ethereum one. And the third one is called half-path. So a half-path is an approach that is in between hash-based state scheme and path-based state scheme. That's why it's called half-path. And it's more like a database optimization technique, where how it works is basically, when we talk about tri-node, MPT node in the database level, you are representing the node as key value pair. So you map the hash of the tri-node to the actual tri-node object. So instead of using just the tri-node hash as the key, you prepend the tri-node hash with the path to the tri-node. So by doing this, because of how the inner workings of the databases work, you can actually compress the database, right? So it's really like a database optimization technique. So yeah, these are the approaches that Nethermind took. But nonetheless, optimizations are great, but they don't solve the root cause, which is state bloat, right? So no matter how much they optimize it, if we want to solve it, we have to solve it at the protocol level. And when we want to solve it at the protocol level, let's go back to the first principle and really ask ourselves when we look at the number of key value pairs, right? So that you have a bunch of like key value pairs right now on Ethereum is going to keep growing, but how many key value pairs are actually being accessed like in the past 6 months or past 1 year or 2 years? So I asked myself this question about last year, and I did an analysis, and the result is that only 20% were accessed in the past 1 year, and the 80% was left untouched. And it makes sense. Let's say 5 years ago, you were just onboarded on Ethereum as a junior or as a beginner. You were excited to deploy your first contract on-chain, and you deploy it, but what's next? The contract, the data, is kept on-chain, but you're no longer using it, and it's just dummy data, it's useless data. And it doesn't make sense for us or for the node operators or for the stakers to continue to store this data. And we want to find a way to remove them. But at the same time, if a few years down the road, you remember, hey, I want to access back my contract that I've just deployed 10 years ago. Can I do that? And the answer it should be yes. And actually, it must be yes. And so all these things converges to a single goal, which is to how can we remove unnecessary state, but provide access when needed. So when we think about this goal, there were a few solutions that come out to solve state bloat and also to achieve this goal. So we're just going to talk them through one by one. So the first solution is called state rent or blockchain rent, as quoted by Vitalik, about 8 years ago. So how it works is simple, right? Now, when you are submitting a transaction, you are paying a one-time fee to put your data on-chain. After the state rent model, if you ever implement the state rent model, not just you have to pay the one-time fee, but you also have to pay a rental fee, right, to keep your data on-chain for a longer time, right? So this particular state rent model has already been introduced by Solana. So yeah, and let's look at the advantage, right? So the advantages are, okay, fairer cost distribution, because right now, yes, we still have state bloat, but it makes more sense for the validators to keep the data because they are getting paid for it. And it also improve like resource management, because right now contract developers, you have to think about this rental fee model. And for the cons, right? In terms of Ethereum, I would say it's very difficult or close to impossible to implement such a model because, for example, EIP 1559 has already caused such a controversy for the entire Ethereum community, even though I believe it's beneficial. If you ever want to change the cost model again for Ethereum, it's going to cause another round of controversy. And at the same time, this particular cost model is like a taxation, additional taxation for the contracts. So I personally believe that the community wouldn't support this, even though it might be beneficial for like solving the stable issue. And if we ever implement this as well, there are many things that we have to take care of, like when legacy, for legacy contracts, or when contract developers develop their contract, they never account for this type of state rent model in the future, right? So how are we going to deal with these situations? So just overall is going to be a very bad user experience issues, especially for contract developers. Then next, we're going to look at another solution called Regenesis. So this was raised about 4 years ago. How it works is that we will delete the entire state, and we only remain the root hash of the state, which is the MPT, and then we do this every certain interval. So I'm going to illustrate this with an example. You have the state, right, with the root and the root hash. After regenesis, you wipe out the entire state, and you only remain the root hash. And let's say if there's a transaction, you want to access the state again, and you want to do something with it, a transaction right now should contain the operation to change A to something else, and also the witness. So the witness here, I'm referring to an MPT proof, a proof that states that this particular value exists in the pre-regenesis state. So with this, after validation that the witness is correct, then you can append this state back to the current state and do the operation with it. So we repeat this every certain interval. So the advantage here is that it's super clean, right? So we know that there's a certain limit that Ethereum state can grow up until, right? And every year is going to just restart. The con here is that the state needs to be stored somewhere, for whether it's a centralized solution or a decentralized solution like IPFS or Portal Network. Why is because people still have to access those pre-regenesis state in order to create a witness. And the second most important one is large witness size. So when we think about MPT proof, the size could be up to megabytes in size. That's the worst case scenario. But even in the worst case scenario, it's still not feasible, right? I mean, if a transaction can already contain a few megabytes in size of like witness, then how about like 100 transactions? Then if you think about implementing this at a protocol level, it's impossible. That's why we need Verco tree, which I'll explain more later. Next is statelessness. So this is the current direction that Ethereum is heading towards, not just to solve state bloat, but also for other benefits as well. This particular scenario is aiming target towards like how it might be able to solve state bloat. So how it works is that, let's say you have EPBS, which stands for Enshrined Proposal Builder Separation. You basically separate the validators into block builders and block validators. Block builders will require the full state for witness creation, and block validators can validate blocks statelessly, which is what we want. So how it works is something like this. You have the builder with the full state. This builder, the only job for this builder is to create block and also create the witness, right? So when you have these two information, it can be sent over to the block validator, and only with the block and the witness, without the full state, it can validate that, okay, this is correct, and it can append this block to the canonical chain, right? So we can see here, the advantage is very straightforward. Block validators have lower hardware requirement because all the heavy lifting work has been done by the block builder, right? So we can even reach a point where if you are a block validator, you can run the software with your phone, right? So this would encourage everyone to be a home staker or home validator. Then for the con here is that it actually doesn't really solve state bloat, because if you think about the full state, we're still going to have like the state bloat issue. It's just that only block builder have to deal with this issue. And eventually this will lead to centralization because not the number of validators, block validators, and the number of block builders doesn't match, and only a few would want to become block builders in the future. Yeah, and also it requires EPBS, which is a research direction that has been taken seriously in the past few years, but it is still a prerequisite. And finally, we move to state expiry. So this is what I think is the most feasible solution when it comes to solving state bloat, at least for now. And even under the umbrella of state expiry, there are a few variations, which I'll talk about it. So the first state expiry proposal was raised by Vitalik about 3 years ago. So how it works, to put it very briefly, is that you create a new state trie at fixed epoch. So right now, you are shifting from a single world state into multiple epoch-based world state or multiple epoch-based trie. So a state is considered as expired if it doesn't exist in the two most recent epoch, right? And if you want to resurrect or access the expired state again, you have to provide witnesses for it. So this is the very brief summary on how it works. So the pro here is that, yeah, if you have such a model, you are guaranteed to remove the stale state. But the con here is that it's extremely complex. First, you require something called address-based extension, which is a research direction that has been stagnant for quite a few years, and it's also going to cause some level of controversy for like the Ethereum community because you are doing breaking changes, right? It's going to affect user experience in terms of like, I think, wallet. So that's one. And the second thing is that when you are shifting from like a single tree approach to multiple tree approach, how clients are going to modify their software in order to deal with this. It's going to be a huge refactoring when it comes to like their state modules for all clients, I believe. And the third thing is that the resurrection logic for this particular proposal is extremely complex. In the previous like solution that I mentioned, the witness here usually refers to like just a single Merkle-Petrarca proof or Merkle proof, right? But here you are not just going to prove like one thing. You also have to prove like different things. Perhaps you have to also combine the proofs together. So if you check out the original article, it's actually extremely complicated. And that's why I believe like this proposal has been stagnant for the past few years as well. But nonetheless, it still inspired us to create some other proposals. Yeah, the next solution is by BNB Smart Chain, or more commonly known as Binance Smart Chain, last year. So I was involved in this project when I worked with them. How it works is that we introduced an overlay tree mechanism called shadow tree. So this shadow tree is like a metadata layer for the current MPT. So this shadow tree, the only purpose for this shadow tree is to determine if a state is expired or not. Yeah. So for the pros, it's a single tree approach as compared to the previous one, and it's also guaranteed to remove the stale state. But the con here is that it's very, very straightforward. And why BNB Chain doesn't implement this is because large MPT witness size. So if that, yeah, that's why the BNB Chain team would never put this on chain. Next, we finally reached a point where this is, I think, the most suitable solutions as of right now when it comes to like state expiry or tackling state bloat, in my opinion. Yeah, so EIP 7736. So this was written by me and Guillaume from the EF team, or Go Ethereum. So he's leading the stateless team and also Verco tree on Ethereum. So I'm just gonna go through how this proposal will work and why it makes sense, right? So first thing here is that there's this new concept of state epoch that we introduced for this state expiry. So you can think of a state epoch as the measurement unit when it comes to determining how long a state is considered as active, right? So in our proposal, we consider a state as active for as long as a year or 2 state epochs, right? So that's the only thing that you have to remember. And we are also going to implement this during or after Vocal tree if we ever want to be enshrining this into the Ethereum's protocol. And there are a bunch of like good resources out there about Vocal tree on why we want to shift from MPT to Vocal tree. You can check out vocro.info on your browser to access more resources. But to give a brief summary on why we need Vocal tree is first, smaller witness size, much smaller witness size. Just now I mentioned that MPT proof size could be as large as like in megabytes, but in Vocal tree it could be just like kilobytes, right? Which is much more feasible to implement it for the protocol. And it also enables like different features like stateless clients on like Vocal sync, which is like very fast sync, right? So you can check out the resources to learn more about Vocal tree. But here, just gonna go through how Vocal tree structure look like. You have the internal node, which is similar to MPT's branch node, and you also have a new node type called like extension node and leaf node, right? So you don't have to care about like how Vocal tree work, but one thing I'll place our attention to is how the values are being placed together, right? So in Vocal tree, values are actually grouped together in leaf nodes, right? You can see the green ones. So this is different from any other structures out there, even in binary tree or like in MPT. So Vocal tree has this grouping property. So how can we utilize this grouping property to implement state expiry? And the answer is fairly straightforward, right? The only thing that we do, that we change in terms of like the Vocal tree structure in this proposal is basically to add something called last epoch to the extension node. And that's literally it. Like that's literally the only change that we make to the Vocal tree structure. And this last epoch is going to be the metadata to determine if a state is expired or not. And we'll see how the state expiry logic work in the next slide. So how it works is that for every write event, this last epoch field is going to be updated with the value of the current epoch. And for any read/write events, if the current epoch is greater than or equals to the last epoch plus num-active epochs, in our case is 2, a read/write event is reverted because the try node is deemed as expired. So to put it with an example, so let's say the current epoch is 3. And for this example, the extension node, the last epoch value is 1. So that means this particular group of values weren't accessed in the past 1 year, right? So what we can do is to mark it as expired and prune them or delete them from the software or from the client, right? So after expiry, what is left is only the commitment of the expired extension node. So the commitment is basically like a hash, right? So just looking at this illustration, you can really see the effect of the state expiry because we are deleting data in this case. So in order to resurrect the value, we introduce a new transaction type called resurrect TX type. So this new transaction, when you are trying to resurrect a value, an expired state, you should provide the path to the expired node, the last epoch value, and also the values in the leaf nodes. So because you are trying to resurrect something that has been expired, so you should also get charged for it in terms of gas. And to validate the transaction is also fairly straightforward. You can reconstruct the expired node from the resurrect transaction. You then calculate the commitment of the reconstructed node. Then you compare the commitment with the one in the Vocal tree. And if it's the same, then it's valid. Then resurrection is completed. And in terms of like pros and cons, the pro is that, again, it's very simple to implement. No ASC is required. Smaller witness sizes. Single tree instead of multiple per epoch trees, comparing to the previous proposal. Smaller resurrection proofs as well because you are just going to provide the necessary data. Clear gas costs, and it's also forward compatible because ASE, or if you want to ever have like ASE or like multiple trees, they are still possible. But the con here is that not all stale data is being removed because there will be a certain case where if you have a group of values, let's say only one of the value is being accessed actively, but the others weren't accessed at all. So in this scenario, this group of value is still will not be considered as expired. So yeah, not 100% effective, but we have to do an analysis on how effective it is on real mainnet data. But yeah, a summary, right? So we are sort of at a point where everything is kind of fine, even though the state is growing like crazy. But we might be eventually reaching a point where things might get a little bit shaky, and home stakers might not be able to deal with this, the state growth anymore. So, and we have also looked at like different solutions from like regenesis, state rent, statelessness, and different variations of state expiry. Each solution, it has its own trade-off, right? They are not perfect at all. Some would not be very effective. Some would be very complex to implement. Some would also affect user experience. But nonetheless, I think why I wanted to have this talk to illustrate all of these solutions is to raise an awareness, because I believe not many people is working on this research area. So yeah, hopefully it sparks some idea on how to like tackle state build and state growth in general. And I guess the final quote is, let's work towards making Ethereum more sustainable and enduring for generations. All right, thank you.
All right, thank you very much. Are there any questions?
Now, I wanted to ask about your opinion on a very simple solution, right? So you said 80% of blocks or transactions were not recently used, right? I imagine most of those are probably in old blocks. Correct me if I'm wrong. So I would imagine that just light nodes, right? Synchronizing some portion of the recent blocks, right? And then perhaps some off-chain service, kind of load balancer that is delegating you either to light node or the full node based on the thing that you want to interact with. What do you think about this?
Yeah, I think the concept of light nodes, it exists, but it only exists for, they are good for like a very specific purpose here. But when we talk about like solving state build completely, we want to solve it for validators. So that means that if we, let's say, can reach a scenario where light nodes can also validate blocks and transactions, then that would be an ideal scenario. But to do that, for now, you would require the full state, right? So it's not possible to have light nodes to be able to validate, even though they are good for other purposes, right? But that's why I say that there's no choice but to actually deal with the full state at the protocol level. Yeah.
All right, thank you very much. And one more round of applause, please.